Hello everyone and welcome to a new episode of All Things IDA. In today's episode, we're going to be going over the CTF challenge from Hex-Rays because it so happens it presents a very nice opportunity to talk about solvers, SMT solvers. So we will cover these three solvers, just like a quick introduction and how to use it to solve this CTF. Okay, so let's understand the problem. The first thing is download the challenge, disassemble it. It's an ELF, so I need to run it in the proper environment. So this is how the challenge looks like if we just run it. The first thing, it displays a message. You need to give a password as an argument. And we will verify all of this when we look at the code. So let's just pass some argument. We don't know anything yet. And here what we get is wrong place. You have to look somewhere else. Okay, so as it seems, if we pass the right argument, we should be having maybe a different message or behavior. Now we can switch back and look at it in IDA. So now let's go back to IDA. IDA directly identified main, so we're good to just hit tab and start decompiling. We can see they're using SDL. Init image, create renderer with these dimensions, and then they check the command line arguments. So if we don't have any command line arguments, that's what we see, basically, that's the message. Then they take the argument into v3. We can safely call this password. And now we can see some assignment here, over test equals 0, and then string copy 2 dest up to 24. So dest, let's see what that should be in a character array of 24 characters. Here we can see IDA did not guess correctly. So let's just simply change the prototype, give this 24. And so we fixed the destination. We can call this actual password. So the first thing they're doing is they set the password to 0, copy it from the command line argument, and here we start to see some checks, and let's look at them. So what they're doing is taking 16-bit numbers out of those offsets, doing some computation, and checking if they sum up whatever the formula is here to that number. If it's not, let's see what happens. So it goes to label 4. We look at label 4. It calls this function. Let's take a look at that function. Prepare read-only buffer for use with other operation. But most importantly, the argument here is size and void mem. So refresh. So they load this here, and then apparently they want to render it as a texture. So that could be explaining the picture that we see, the first error picture. Wrong place, look somewhere else. We can verify that if we go to that buffer, and we also have the size. If we follow it, we can see the PNG header. And also IDA, since a couple versions, allow us to visualize this with an additional plugin it ships with. So here the open picture really maps to a plugin that's installed. So we can say open picture, and it does render it inside IDA. So here we have it. That's the wrong place. That's the wrong image. We should have something else. But we can call this bad PNG, for example. And from the size, we can also just create a proper array. So if we go back to IDA now, we see if the formula for the password contents, the first part. So we'll notice there are multiple checks. But if it doesn't meet the condition, it seems it's going to be loading the bad PNG. So let's call it here bad password. So they load a picture, they create a texture out of it, eventually they render it. All of those conditions, bad password, another condition here as well, bad password. So there are multiple conditions that can take us to the bad password. So our goal is, how can we find a password that can fulfill all those conditions. And that's where we start talking about SMT solver or theorem provers. So the first condition is well, the password at those should have that condition, this one. There are more conditions that we have to look for. We can safely ignore the transformation in between the checks. So here we have multiple checks, then some decryption on the correct buffer. We can skip it because the transformation we see here does not change the input password. It just reads it. So we can do all the checks even before doing any transfer. We can reorder this. So let's also skip that decryption loop here and take one more condition. So that's one more condition we need to pass. And let's see. Then there is another loop as well. And that loop is as well doesn't change the password, it reads it, so we can skip it. And that's the last condition. Let's try to pass that condition as well. So these are all our conditions. And here we can say if it's not equal, also go to bad password. So our problem is all about finding a combination of numbers in the password. So if we have here character password of 24, we have to find all the proper values that will pass, that will never go to a bad password. How can we do that? That's where we will use something like theorem provers. What I'm going to be talking about is the Z3 framework. It's called Z3 Theorem Prover, and it's from Microsoft Research. Now, there's so many other theorem provers. This one is popular, free, and works with other frameworks we will be using in the future. To install it, it's really simple. All we have to do is say pip install Z3 solver. Okay, so now that's installed. Let's formulate a simple problem just to give you an idea. So this is our goal, but let's put that aside for now, and let's assume the condition is simple. Let's suppose we have two numbers, x and y, and the problem was simple. Like there are some checks here, like take input from x and y from the user. Then the check is simple. Let's say if x times 2, let's say plus y times 5 equals some number, for example, can we find such a value? Then that's the good password. So this is a simpler problem to solve if it's satisfiable. So here comes the concept of satisfiability. Can we, given those constraints, so this is a single constraint here. The constraint is just a condition that x times 2 plus y times 5, can we find such a value that gives us this number, for example? We can try. And if we can express ourselves using these three to solve this, we should be able to fulfill that more complicated set of conditions. So here we have 1, 2, and 3, 4, 5 conditions. Here we have a simple condition, one condition. How can we express this condition? So I'm gonna go here. Let me see now if Z3 is available now. Okay, so I import Z3, it works. So we import Z3. The first thing is we need a solver. So I'm gonna use the variable solver and grab a solver instance. That will be holding all the constraints per the solver. The second thing is we need to define our variables. So let's suppose we're looking into the integer space. So I need two variables. I want x and y. And so I would say I need two integers. So this is the syntax for Z3. And now that I have those variables, let's add the constraint. So now we go to the solver object and we say add. My constraint is if I multiply x by 2, then add to it 5, can we find such a number? This is the first constraint. So I added the condition using these three variables. Now we can ask, is it satisfiable? So we can say, let's say, if solver.check equals satisfiable, we can say solver.model for now, and let's print everything, all the variables that fulfill. Otherwise, no solution. We cannot find any x and y that satisfy that constraint. Potentially, because they're ints, maybe I will not find for this constraint, but let's run and see. Here it found, for example, 525 with y equals 0 is a potential solution. Let me take this to another snippet, run the same solver, but this time I'm gonna add to the solver, maybe find another solution. So I'm gonna say solver.add another condition, that is x should not be 525. By adding one more constraint, this is the total. This is the whole list of constraints. The first constraint is what we added initially, x times 2 plus y times 5 equals this number. And then we added also x should be different. That means if we try to find another solution, it will avoid that because that's part of the new constraint. So let's see if we can satisfy this. Here we found if we put x0 and y to 210, for example, now we can also iterate to the next solution. Y not equals 210. Let's run it and see if we can have one more solution, and so on and so on. As you can see, the more constraints we add, and then we can check if it's satisfiable or not. That's really the gist of it. We create a solver, we introduce the variables, and we add the constraints, and we let that solver try to, in an optimized manner, find a solution. So how did I learn these three? From many locations, but the most useful ones I found were the one from Eric Pony, Z3 API in Python. It starts basic stuff, create the variables, add the constraints, and so on. It has very nice examples, straightforward stuff. It has puzzles, for example, like the 8 queen problem, Sudoku. So that's the first reference, I would say. And the second is from the work of Denis Yurichev. Did a nice free ebook. If we now go back to our challenge, we need a way to express all those conditions. Very simple. That's all we want. We want 24 characters, so we want 24 numbers, and then we will have simply solver.add that condition and so on. And for this, to save time, I have already prepared the solution, so I'm gonna just go over with you and explain it. So the first thing is I import from Z3, and then I create an array for the password characters. I use the constructor here bitvec to specify it's a vector of bits 8 to designate it's a character. So all I did is I created 24 8-bit Z3 variables. So every bitvec will represent a character in the password. Then after I created the variables, I need to add constraints. So what are the conditions for those individual cells in the password? So create a solver. I need to make sure I don't search the whole 8-bit space. I need to search in, let's see, stuff you can pass from the command line. So A to Z numbers and some punctuation characters. And then after that, I introduced a bunch of helper methods to let me express such a thing. So since password is a character, here we can see the C syntax to actually extract 16 bits of a given location. And here I'm using the same. I'm using these three functions. By doing this, I can express the C expression like that, as we will see. And now that we have the helper methods, we can try to express the constraints that we want to solve using these three. So let's look now how we can express ourselves. So we spent a lot of time explaining what's the problem. Now let's see how to use a solver to solve it. So after we added the constraints for our character, for our password, printable characters and punctuation, the additional constraints are the following. So the first one is it's using word access. So we need to translate this whole constraint to a Z3 syntax. So here the first constraint we're adding is words of 8. Now we see 8 because here it's 16 bits, so really that's like 16 divided by 2. Words of 11, this is words of 11, 22 divided by 2. So word of 8 plus word of 11 minus word of 4 minus word of 7 as well, because we are just dividing by 2 to access the word from a word array. This is a byte access, so that's why we have double the index. So the first condition is expressed, and also we want to make sure we're comparing with another 16-bit number. So compare it with a constant. So that's how we create a constant in Z3. It's a bit vector with a value. The value is this number, and the size of the bit vector is 16. Then comes the second constraint, which is as well this line. Same story, the indices is just here, we divide them by 2. So word of 5 and equals that bit condition. Another one is this here. Basically, we want password of 16. So this is directly divided by 8, which gives us Q words of QD words of 2. Should be, once we XOR it with password of 0, it should give us that 64-bit number here, the exact number. Another constraint for D word access, so here we have D words, as well, password of 20 divided by 4, because of a D word, so here 5, password of 0, 2 times password of 0, and D words of 16 over 4, so D words of 4 shifted to the left. And so all we did is we really one-to-one mapping, convert the pseudocode conditions to these 3 conditions. So this one, this is the last condition here. Q word of 8, so Q word of 1 equals pass 16 of 2. So here as well is as well that 64-bit value. Once we add all the constraints, we want to find all the solutions if there are more than a solution. So we do a loop while for that solver, given those constraints, while we have satisfied. Then let's grab the model. This will give us all the values of the characters that the concrete value, one possible solution that satisfies all of those. We go over the model and we ask for a concrete value. Just give me the value for that symbolic representation. So this should be the whole script to solve that. So let's try it out, load it and run it. And it took a while, it took a couple seconds, but once the script finished, it displayed that this password potentially satisfies the condition. So let's try. So that's the challenge. This is the password. Let's run it. And here we go. Actually, it does show us something different this time. And that's the full decrypted message correctly. So that's it for today. I hope this introduction to SMT solvers was approachable and good enough. Hopefully in the future we'll have more advanced stuff and slowly build our skills using those frameworks. Thank you and see you next time.